So one of the reasons for organizing this video conference is that a lot of students have questions. Some of them have been answered in the forum, but some have not been answered. So I felt that having a one-on-one interaction would be better. So nptel office was very glad, they're very helpful in organizing this, and I also thank all the colleges for helping to organize it. So what I have here is a list of questions sent to me by one particular college. I think it's MAM College of Engineering and Technology. I don't know if they are part of this video conference here or not. So if you guys are already here, maybe you can raise your hand so I know which college it is. What I'm going to do is maybe try and answer some of these questions. If they have already been covered, these questions are similar to the questions you guys have, then it's good. And if there are any extra questions, then we can sort of do a one-on-one kind of interaction, maybe go from one college to the other. Okay, so I also have here, I think as part of the tablet, an application where I can draw stuff, and I believe that will also be projected. So if you don't see me and you see me drawing something, then I'm using that application. So this is the first time I'm doing that, so there will be some initial hiccups from my side when I get familiarized with this video conferencing procedure, and we'll see how things go as we go along. So I'm just reading out the question. They have around 10 questions, and I will try to answer each question in brief. So the first question is, how do electrons obey Fermi-Dirac statistics? So some of this question basically assumes that you have some knowledge of solid-state physics. The idea, which is something that we don't cover in the course. The most important thing to remember is that electrons obey what is known as Pauli's exclusion principle. This is because they are charged. So you cannot have more than 2 electrons having the same set of all 4 quantum numbers. So if you think about an electron in an atom, in an orbital, each electron is characterized by 4 quantum numbers, and you cannot have more than 2 electrons having the same set. So you will find 2 electrons with N, L and M being the same, but their spin will be plus half and minus half. So starting from there, it is possible to derive the Fermi-Dirac statistics and show that an electron actually obeys it. So that is something that's beyond the scope of this course. If you do physics of materials, or if you've already done physics of materials, some of it would be covered there, or any solid state physics course, they will cover it. So as far as this course is concerned, we will just say that electrons obey Fermi-Dirac statistics. So the second question is, why is the Fermi level close to the conduction band for n-type and closer to a valence band for a p-type? So one way, of course, is you can use the equations and show it. So let me go to the board here. So let me go to the board here. So for example, if I, so let me have a semiconductor. We know this is the conduction band, this is the valence band, and this is the band gap. So if I have an intrinsic semiconductor, usually my band gap is somewhere in the middle. I have something called a vacuum level, and the distance between the band gap and the vacuum level is called the work function. So work function is nothing but the amount of energy required to remove an electron from a solid. If I have an n-type, I have more electrons than I have holes, so it must be easier for me to remove my electrons, which means my work function is lower, or the Fermi level shifts closer to the conduction band. On the other hand, if I have a p-type, I have more holes than electrons, so it must be harder for me to remove these electrons, which means there is an increase in work function and the Fermi level shifts lower. So you can argue based on the work function, or more simply you can just argue based on the equations. So this is for an n-type. And this is for a p-type. So you can argue based on the equations, or you can argue based on work function. But because you have an imbalance in electrons and holes, that is why you have the shift. So question 3 is what is meant by lattice scattering and dopant scattering. Again, we don't go much into detail as far as the scattering goes, but the idea is that if I have electrons or holes moving in a solid, they basically see the effect of the lattice, which means they're going to see that the lattice atoms that are vibrating and they scatter. That is lattice scattering. If you have dopants, dopants can either be positively ionized or negatively ionized. In that particular case, that can also cause a scattering because of an electrostatic interaction, and that is dopant scattering. Both of these have the effect of lowering the mobility of the electron or the hole. So question 4, does PN junction act as a rectifier only in forward bias? So the definition of a rectifier itself is that it conducts only in the forward bias and not in the reverse bias. So yes, so PN junction does act as a rectifier. It conducts only in the forward bias but not in the reverse bias. So question 5 is about heterojunction diodes. And whether heterojunction diodes can be used for practical applications. If you come to the last part of the course, so week 7 and week 8 lectures, where we look at optical properties of LEDs or lasers, or when we look at photodetectors or solar cells, heterostructures are used a lot for those applications. We only look at the basics of heterojunctions or heterostructures as far as this code goes, but the applications are essentially on the optical side. So question 6. Whether the defects in material affect the reverse saturation current. In this particular course, when we look at a PN junction IV characteristics, so I and V, so let me just redraw this. So this is my forward bias and that's my reverse bias. So we said that the forward bias current increases exponentially with voltage and the reverse bias current is a constant. So one of the assumptions when we say this is that we essentially have a case where in reverse bias the bias voltage does not play a role. So we ignore the effect of both the defects in the material. Defects can affect the value of J0 by basically affecting the mobility, but we also ignore the bias in the reverse case. So this is an assumption where we only consider an ideal junction. If you have a real junction, then increasing in reverse bias voltage will lead to a slight increase in the current, but as I said, we only look at ideal junctions in this case. So question 7 was about the effect of applied voltage on reverse bias. So I've answered that along with question 6. Question 8. In fact, many students even here in IIT also have the question, what is the difference between a Schottky junction and a PN junction? So this particular diagram was for a PN junction. I can draw a similar diagram for a Schottky junction. So both Schottky junctions and PN junctions behave the same. Both are rectifiers in that you have current in one way and you don't have current in the reverse bias case. The main difference between PN and Schottky is one is the rectification ratio. So rectification ratio nothing but the current in forward bias for some voltage. Say rectification ratio is nothing but the current for some voltage in forward bias for the current in the same voltage in reverse bias. So PN junctions have a much higher rectification ratios than Schottky junctions. More importantly, in the case of Schottky junction, the reverse saturation current depends upon the metal and the semiconductor and the Schottky barrier. So once I fix these, my reverse saturation current becomes constant as far as the Schottky junction goes. But if I have a PN junction, the reverse saturation current not only depends on the material, because the equation has Ni in it, so this is for a PN junction. So it not only depends on the material comes through Ni square, it also depends upon the doping concentration, Nd and Na, which in turn affects both the length and the diffusion coefficient. So in the case of PN junctions, it's possible for you to change your Js naught by changing the doping concentration in the materials. Well, this is not true in the case of Schottky junctions. So these are some of the main differences between Schottky and PN junction. Question 9. What is the critical radius in calculation of kinetic energy in extrinsic semiconductors? I'm not sure if the question refers to the either the doping concentration. I assume that's what the question is. So when we look at semiconductors, especially extrinsic semiconductors, so let me take an example of an N-type semiconductor. So this is EC, EV. We say that you have donors, and these donors are located very close to the conduction band. This is my donor level, and this is very close to the conduction band. This energy is usually of the order of say 50 milli electron volts, if you just pick a number. So if you notice, I have drawn EC as a straight line, EV as a straight line, but the donor level as essentially dotted lines. This is because the donor levels are localized. They are localized levels and they don't form an energy gap. But if I keep on increasing the concentration of the donors, there is going to come a time in which the donor levels will all overlap, and instead of a dotted line, I'm going to have an energy band. So again EC, EV, and I can have a donor band. So I'm going to show that by the shaded lines. We call these type of semiconductors degenerate semiconductors, in which case your donor concentration is so high that you have an energy band. So we have a transition from localized states to degenerate states. So there is a critical radius, and related to that there is a critical concentration which you can calculate to tell you at what point you have localized energy states or degenerate states. As far as the scores goes, we are mostly dealing with low donor concentrations, so these are all localized states, but we can also calculate the critical concentration for degenerate states, and this is again related to calculating the Bohr radius for the donors and then taking a volume and inverting that to get the concentration. So some of this information is there in the notes in extrinsic semiconductors. So rather than me trying to work it out here, you can go and look at it. If you have any specific questions later on, I will also answer that. So the last question. This is from the set that was submitted, is what is the depletion width for highly doped and lightly doped PN junction. So we can relate the depletion width to both the dopant concentration and the potential. So let me just check the formula so I have it correct. I'm just rewriting the formula. So this is the equation for the depletion width. So we find that the depletion width depends upon Na, Nd, and also the product. So if Na and Nd increase, the sum will also increase, but more importantly the product will increase faster. So if I have higher doping, my depletion width is lower, and if I have lower doping, my depletion width is higher. So when we compare highly doped and lightly doped PN junctions, the main difference is that as I increase the doping concentration, the depletion width will reduce. So these are some of the questions that were asked. So what I will do is I will stop here, and then we will have a sort of interactive session where you guys can ask your questions, and then I will try to answer them either using the blackboard here or directly.
Hello, sir. Good afternoon, sir.
Yeah, good afternoon.
Good afternoon, sir.
Yes.
Myself, Kumar Swami from KSRCT.
Okay, go ahead.
KSRCT, sir.
Okay, go ahead, please.
So my question is regarding solar cells, sir.
Okay.
Sir, can we fabricate a solar cell that can absorb whole solar spectrum, IR, visible, and UV? Is any solar material? Can we make it in a solar cell? Yes, sir.
Okay. Okay, so I'll try to answer your question. So the short answer is yes. You can fabricate solar cells which can absorb all of the regions. Question is whether you really want to do that, how expensive that is. We will not take it up now. But here's the main thing, right? You basically want a material whose band gap lies in the IR region, because that material can absorb both UV and can also absorb the visible. So you want a material with a band gap in IR take silicon or germanium or gallium arsenide, there will always be some regions of the spectrum where it will not absorb. So if you make, say, a Schottky junction with such a material, you can also absorb energies below the band gap by what is called as an internal photo emission. So yes, it is possible to design a solar cell like that, and we can use something like germanium. There are even materials with even lower band gaps. How efficient it is, that is a different question to answer. But to your question, yes, it is possible to do that. Next question.
Also, can I proceed, sir?
Yeah, proceed. Please go to the next question.
Yes, this is a very basic question I asked. I have a small doubt, sir. In
Okay.
school itself. We say that holes, atoms lose in less electrons. Can we say that holes, atoms with lacking electrons? Can we say it as holes, sir?
Can you just repeat the question? It is not very clear. Atoms with what?
Holes means, I learned what is holes means atoms with lacking electrons.
That is correct.
correct, sir?
So we don't talk about atoms, we talk about solids. So when we talk about electrons and holes, we are not dealing with individual atoms. We are dealing with a solid with hundreds and thousands or 10 to the 23 atoms. So we say hole is a lack of an electron in a particular energy band, not with respect to an atom. I haven't come across anyone who describes holes like that. So I would say it will confuse you if you think of holes with respect to atoms. Think of holes always with respect to an energy band in a solid. Does the answer help, or do you have a follow-up question? Was it clear, or do you have some more questions?
Yes, sir. That means band means you say that we can think that collection of atoms like that. Bands means
Energy band is nothing but because of the collection of atoms, you have lot of energy states. So all those energy states put together, that is your energy band. Anyone else can go ahead with their questions, please?
Sir, can you hear me, sir?
Yeah, I can hear you. Please go ahead.
Sir, can you please be much more precise where to use Schottky and PN diodes, sir?
Where to use?
Schottky diodes and where to use PN diodes?
So where do we use Schottky diodes and PN diodes? Really, I don't have a very definite answer in terms of applications, because it is not just the material, but there are other things that go into the choice of where you use the diodes. As far as I know, most semiconductor applications end up using PN junctions. There are some applications, especially even in the terms of solar cells, where they use Schottky diodes. So, for example, most solar cells are essentially PN junction diode based, because you have a lot more control over the properties. But it doesn't mean that Schottky junctions cannot use. You also have Schottky junction based photodiodes and Schottky junction based solar cells. In fact, in our own research group, we are working on a Schottky junction based solar cell. So in terms of what people in the industry use, I don't have a very clear answer. It just depends upon the nature of your application and how easy is it for you to get those materials.
Hello sir, I'm Shantini from Ma'am Set sir.
Okay.
I have a doubt in how to calculate the depletion width, sir.
Okay. In the case of a PN junction, right?
Yes sir.
So I don't know if you can see the board which has a set of equations on top. Are you able to see that?
Yes sir.
So in that, the last one, which is W, and there is a formula under square root, that is essentially the depletion width. So if you have a PN junction and you know what your Na, which is your acceptor concentration, and Nd, which is your donor concentration, you can go ahead and calculate. So the main thing you have to remember here is that to get all of your units correct. If you see all of my questions, I will give you Na and Nd in per centimeter cube. So let me see if I can write it down. So Na and Nd are usually per centimeter cube, in which case your epsilon naught should also be in per centimeter. So once you have that, then you should be able to calculate your W. So as long as all your units are correct, you should be able to use this expression and calculate W. Does that answer your question?
Yes, sir.
And if I have a forward bias, so just to follow up, if I have a forward bias, instead of V naught, I will use V naught minus V external. So the depletion width will reduce in forward bias. And if I have a reverse bias, my depletion width will increase. So I will use V naught plus V. But either way, the equation remains the same.
Okay, sir.
Okay?
Thank you, sir.
Thank you.
Sir.
Yeah, in fact, we were just I also teach this course here in IIT Madras, so we were just discussing this forward bias and the depletion width in a PN junction yesterday. So students had the same question, so this is the answer. Just use the formula and make sure your units are all consistent.
Hello, sir.
Okay,
I am Mahalakshmi. I am from MEM.
Okay.
How to calculate energy gap and what's the purpose for energy gap calculation?
Okay. So energy gap of a semiconductor, right?
Yes, sir.
So energy gap calculations are made, but again they require very advanced knowledge in solid state physics, which is way beyond the scope of this course. So people do energy gap calculations. The reason they do it is especially if you're designing a new semiconductor, you want to know what its properties are before you actually go ahead and fabricate devices out of it. People also look at for example, if I take something like gallium arsenide and aluminum arsenide, if I mix them and form aluminum gallium arsenide, the band gap and the energy band will change depending upon how much of each I take and mix. So there are calculations that people do in order to check this. So there are some applications for energy band calculations or energy gap calculations, but again, doing actual calculations is way beyond the scope of this course. It requires an advanced knowledge of quantum mechanics and also advanced computational physics.
Thank you, sir.
Okay, thank you.
Yeah, ma'am, just hold on. MEM CET, please just hold on.
Okay, sir.
Devi, please go ahead.
Hello, good afternoon, sir.
Good afternoon, please go ahead.
Sir, what is mean by compensation doping? Could you please explain us with an example, sir?
Okay, so that's actually a very interesting question. So I will go back to the board and explain the compensation doping. So let me say I have a p-type semiconductor. So I'm going to start with p-type silicon with a certain acceptor concentration of 10 to the 15 centimeter cube. For silicon Ni is 10 to the 10. So this is a p-type semiconductor. So my whole concentration is just Na, which is 10 to the 15. And my electron concentration is Ni square over Na, which is 10 to the 5. So now to this semiconductor, let me add some dopants, let me add some donors. So these are N-type. So we started off with P-type and now we are adding N-type, and this concentration is 5 times 10 to the 15. So it is more than Na. So in this particular example, I have both acceptors and donors. So these are called, so this is an example of compensation doping. So since I have more number of donors than acceptors, my electron concentration is Nd minus Na. So it's 5 minus 1 times 10 to the 15. That's 4 times 10 to the 15 per centimeter cube. My whole concentration is Ni square over N. So 10 to the 20 2.5 times 10 to the 4. So I started off with a p-type semiconductor, but because I've added more donors, I have made it into an n-type semiconductor. So this is an example of compensation doping. The reason why we do compensation doping is because I can use this in order to form things like p-n junctions. Okay, does this help you?
Yes, sir. Good morning. Good evening, sir. This is Vimalraj from MAM.
Okay.
Sir, my question is that, sir, how can you calculate slope when we are given with the reverse saturation current?
How can you calculate what? The slope?
Slope. Particularly not, sir, but this is a general doubt.
So slope of I versus V, right?
Yes.
Okay. So I know that the slope calculation came as part of a question. So let me just go to a new page.
Okay, sir.
So the slope is nothing but you take any particular point,
Yes.
and you draw a straight line. And that's essentially a slope, right? As far as the question goes, there is a way to calculate it. So let me just use I instead of J. So your equation is I equal to I naught exponential EV. In that particular question, we had an ideality factor, so there was an eta term. If not, you don't have to have the eta term. So I take log on both sides. In most cases, you plot log I versus V. So it's log of I naught plus EV over eta kt. So if you look at this, this is nothing but an equation of a straight line of the form y is equal to c plus mx. So c is your constant. This term e by eta kt is your slope, and x is v. So for a log I, versus v plot, your slope is nothing but e by eta kt. So your reverse saturation current I naught or J naught is part of the constant. It doesn't come in the calculation of the slope. Does this answer your question? If you have a general thing, then you have to calculate the slope at that particular value.
Okay, sir.
Okay?
Okay, sir. Thank you.
So next person.
Yeah, RGCT, can I take the question, please?
Hi sir, I'm Hemlata from RGCT.
Okay, please go ahead.
Sir, in transistor module, you have said that the width of the collector is always larger comparatively to base and emitter. Is there any reason for that, sir?
It is just that your current goes from the emitter through the base to the collector. So whenever you have current, you always will have some heating associated with it. That's essentially I square R. To reduce the heating, you want a lower R, so you go for a wider region. So it is just in terms of a practical device reason rather than any fundamental scientific reason. Okay?
Sir, another question, sir.
Okay, please go ahead.
Why carrier concentration increases when doping level increases?
When doping level increases? So when you say carrier concentration, you mean the majority carrier concentration, right? So if it's donors, it is n type, it is electrons, and if it is acceptors, it is holes. That's what you're asking about, the majority carriers, right? So again, as your doping level increases, all of these dopants will get ionized, which means more number of electrons will go to the conduction band if they are donors, and more number of holes will be formed in the valence band if they are acceptors. So as long as all of these dopants are ionized, your concentration will increase with your doping concentration. So at room temperature this is true, but this is not necessarily true when we go to low temperatures. But most of us, we work in room temperature, so we can say that there is a direct connection. Okay, thank you.
Sir, KSRCT is back. RGCET, Vagdevi.
I think MAM have something, so yeah, if you can go ahead and ask, maybe then we can come to.
Sir, I'm just unmuting myself. MAM, you are unmuted. Please go ahead.
Yes, sir. This is another question. Sir, what is carrier diffusion length? Let's understand.
What is
Minority
what?
Minority carrier
diffusion length. Okay. So that's also a very interesting question. So again, let me go back to the notes. So if you look at a PN junction, so let me just draw a PN junction. I'm only going to draw a schematic. So I have P, I have N, and I have a certain depletion region. So when I am in equilibrium, I essentially have no current. Now I try to bias my PN junction by connecting P to the positive and N to the negative. Right, so this is a case of forward bias. In this particular case, electrons will flow in one direction. The current, or if you want to think about it, holes flow in the opposite direction. So I have holes that are injected from the P side onto the N side. Same way I have electrons from the N side that are injected to the P side. So electrons are injected to the P side and holes are injected to the N side. So these are essentially minority carriers, right? So electrons are minority carriers on a P-type semiconductor. Holes are minority carriers for an N-type. So obviously at some particular point, these electrons in this case will basically get destroyed by combining with a hole. These holes will get destroyed by combining with an electron. But before they do that, they can travel a certain distance. So this distance is called your diffusion length. And because these are minority carriers, they are called minority diffusion lengths. So this length is proportional to square root of the diffusion coefficient times a time. The time is called the minority carrier lifetime, and same way LH is DH times tau H. So that is where the concept of minority carriers essentially come into play.
Okay, sir.
Okay.
Okay, sir. Okay, sir. Okay, sir. So then another. So the lifetime is only to the recombination time is taken as lifetime, right, sir?
That is correct. The recombination time is the lifetime.
Okay, sir. Thank you.
Thank you. So maybe go to another college.
Sir, in semiconductors we are talking about electrons and holes. So originally electrons we know they can move from one place to another place. So we are calling as electron current.
Okay.
But holes, as far as considered, they are not moving at all. But somehow we are calling as hole current. We are saying that both electron current and hole current is possible. That is majority current and minority current. So what is this hole current? Exactly what is the physical meaning of that?
Okay. So there are differing opinions on this. I will not say that holes do not move. So I will still say holes move. But the most important thing to remember is that a hole is not a real thing. A hole is nothing but the absence of an electron. So if I am saying the holes move from left to right, it essentially means that electrons are moving from right to left. So some people talk about a hole current, some people just use electron currents, with the idea that we know that holes will move in the opposite direction. But hole is nothing but a mathematical representation for us to simplify the problem. They're not real. Like electrons, you cannot track holes or you cannot measure other properties of holes. It is just a construct for us to explain the behavior of semiconductors. Okay? Is that clear?
As far as the band energy diagram is considered,
okay,
so holes will be there in the lowest energy band and electrons will be there, free electrons will be there in the conduction band.
That is correct.
So sir, how can we say what is the speed? That is whether electrons are having highest speed or holes are having highest speed. Can we elaborate with the band energy diagram?
So which of these have the higher speed? Again, it's kind of it depends on the system we are essentially talking about. So if we go back and try to draw an energy band diagram. So this is my valence band. This is my conduction band. So what happens is I have electrons in the conduction band, and obviously I have an electron and that's my hole. Let's say I have an electric field. This side is positive, that side is negative. So electrons will move in one direction and holes will move in the other direction. So if I look at the conductivity is Ne mu E plus Pe mu H. So mu E and mu H are indicative of the mobility of the electron and hole. So if I look at silicon, mu E is 1350 centimeter square per volts per second. Mu H is 450. If I look at gallium arsenide, mu E is 8500 I think centimeter square per volt per second. Mu H is much smaller. I don't remember the exact value, but it's somewhere less than 1000. So if you take the mobility as an indicative of how easy is it for the electrons or the holes to move, you can see that in both silicon and gallium arsenide, mu E is higher than mu H. I don't know if you can generalize this and say that for every semiconductor, mu E is always more than mu H. There may be exceptions to this rule, but you can use mobility as sort of an indicator as to which moves faster. Again, I would not like to use a speed term because the speed will also depend upon the value of the electric field, but you can use mobility as a substitute for speed.
Sir, you talked that when electrons jumps from one point to other point, then holes are being generated. So
Okay.
holes are nothing but the empty spaces where the electrons have been gone to other points.
That is correct.
So virtually the speed of the electron and that is I can say the mobility of the electron and mobility of holes must be the same.
No, that is not true. The reason is these electrons we are talking about, they are in the conduction band, and the holes are moving in the valence band. So they are moving in different energy bands in the semiconductor. So they have different energies. So their mobility should actually be different, not the same.
Sir, can I attribute that due to heavy traffic in the valence band, probably hole mobility may be less compared to the electron mobility in the conduction band?
You can talk about it, but I don't know how scientific the description is. So I would rather use the word mobility rather than talk about speed or traffic. You can link this to say the lifetime. You can also link it to the lifetime is, or you can link it to the scattering. But yeah, I would rather just say that the energies are different and the energy landscape is different in the conduction and the valence band, and that is why you see a difference in the mobilities.
Sir?
Thank you.
Thank you. Maybe you can go to another college. So MAMCET?
No, sir. RGCET has been waiting, sir. MAM,
Okay,
please wait.
so we'll go to RGCET first and then come back to MAMCET. Okay. So RGCET, can you go ahead, please?
Hello, sir. I'm from RGCT.
Okay, please go ahead.
What are low K elements? On what basis they are grouped as a low K?
Low K elements.
What do you mean?
What exactly is K here? Are you looking at a dielectric constant or are you looking at something else?
It's dielectric constant.
Okay, so I don't know about low K dielectric elements. They are usually compounds that are low K dielectrics. Again, is this with reference to any specific application you're looking at or something else?
Yes, it's there in video.
Okay, so if it's there in any particular lecture, you can send it to me and I can respond to you specifically. Usually in the case of semiconductors, low K dielectrics are used as interlayer dielectrics when we talk about metallization. So if I have two layers, let's say two metal layers, and I need to insulate them, we usually use a dielectric in that case. So whenever we have a dielectric, we also have an associated capacitance, and we usually want devices with low RC values. So for having a low capacitance, you typically want a low dielectric constant or K, and those are your low K elements. So that's a general answer, but if there is something specific in the video, again just send me an email and I'll take a look at that and then respond to you specifically in what context I use it. Okay, thank you.
Good evening, sir. I am from MAM College.
Okay.
Can you explain for me how the electron affinity in the material semiconductor?
Can you? What is electron affinity?
Yeah, yes, sir.
Okay, what is electron affinity? So again, let me just go back to the notes. So if I have a band diagram of a semiconductor, most often I don't draw the vacuum level, but typically you always have the vacuum level on top. So the vacuum level is essentially, you can think of it as a zero energy level or an energy level above which an electron is no longer bound to the solid. So then I have my valence band edge EC, I have my conduction band EV, and if this is an intrinsic semiconductor, my Fermi level is somewhere in the middle. So the Fermi level to vacuum level is called the work function, but the electron affinity is the energy from the conduction band edge to the vacuum level. That's usually called chi. This is electron affinity. So this material were silicon, and if I have p-type silicon, my Fermi level will go down, so my work function will increase. If it is n-type silicon, my Fermi level will go up, and once again my work function will decrease, but the electron affinity will not change. So as long as I have a material, then the electron affinity is sort of fixed for that material. Okay?
Okay, sir.
Sir, good evening, sir.
Okay.
Sir, why silver metal is used mostly in electronic components, sir?
So one advantage of silver, and in fact we also use silver, because silver is one of the best conductors that are available. So among metals, silver has the highest conductivity. Gold is nobler than silver. In fact, gold is less reactive than silver, so a lot of people also prefer to use gold. The problem with gold, of course, is that gold is much more expensive. So as a material, if you're trying to make a device, the cost of the device goes up. copper is also a very good conductor. Almost all integrated circuits use copper for your interconnects. With silicon, copper has a problem that if you don't isolate it, it can basically cause defects and destroy silicon sample. So copper, silver and gold are more or less the three most common elements. Silver is used simply because it is the best conductor and it is not as expensive as gold and it is not as reactive as copper. Does this help?
Yes, sir. So the next will be KSRCT, please.
Okay, please go ahead.
In solving problems relating career concentration, we are so I want one constant.
So
why it is only
in the audio, I heard solving problems related to career concentration. Then what did you say?
in Boltzmann constants.
Okay, so do you want the value of Boltzmann's constant or where we use it? So there seems to be some issue with the audio because I can't hear the full question. And
KSRCT, please type the question. Please type the question on the message pad. Please type the question on the message pad, and I can read it out to Professor.
I think he's. So yeah, please type the question and then I will try to answer.
Sir, Vagdevi to answer the question.
Okay, please go ahead.
Sir, why amorphous metal has no longer range, sir?
Why amorphous has no long range order?
Yes, sir.
Is that the question?
Yes, sir.
So actually the definition of an amorphous material is that it has no long range order. So it's both. So you can't, so if a material has no long range order, it's called amorphous. So it's the other way around. But if you look about most metals, we say they have something called a crystal structure. So if I take something like copper, then we know that copper has what is called an FCC crystal structure. I'm not sure how familiar you are with crystal structure terms. Let me just try to draw it for you. So if I take copper, copper has a cubic arrangement. We call it face-centered cubic. So this is my cube. I have atoms at the corners. And I also have atoms at the face center. So think of all the faces of a cube. You have essentially 6. So you're going to have atoms at the corners and also in the face centers. Now if I take this in a copper solid, I can basically keep on repeating this unit cell and I have what is called an ordered crystalline arrangement. As long as I don't have things like grain boundaries or other defects, all of the copper atoms' positions are fixed. So if I know one copper atom's location, I can basically know the location of all the other atoms. So this is called long range order. In an amorphous material, the positions of the atoms are not necessarily fixed. They are all randomly oriented. So if I know one atom, I cannot predict where the next atom is, or I cannot predict where the subsequent atom is, and so on. So that is why we say amorphous materials have no long range order. So it is sort of a definition of amorphous materials.
Sir, I'm opening the mic for ma'am, sir.
Okay, please go ahead.
Good evening, sir.
Okay.
Sir, can you differentiate me the drain punch through condition and drain induced barrier lowering occur in a transistor, please?
So you have basically drain punch through and drain induced barrier lowering, right?
Yes, sir.
So that is something that we don't necessarily cover as part of this course. When we talk about a transistor, we do say that there is a saturation, and beyond the saturation you have the punch through. I will not use this forum to talk about it in detail because, as I said, it's sort of beyond what we do in this course. If you do have a specific question, write to me and I can point out some reading material where you can discuss this more in detail. But let's not do that here because that's sort of beyond what I expect you guys to know as part of this course.
Okay.
Vagdevi, please go ahead.
Okay, sir. I have a small general question related to electrons, sir.
Okay.
See, if one electron is bounded in a one-dimensional potential box having a size of 4 into 10 power minus 10 meters, what is its minimum energy?
So it's in a 1D box and 4 times 10 power minus 10 meters, right?
4 into 10 power minus 10 meters.
Okay, so once again that's sort of a direct formula application. Energy is nothing but n square h square by 8 ml square, where L is the length of your box. So your length is 4 times 10 power minus 10 meters. So the minimum value of L is 1. So electrons can have 1, 2, 3 and so on. If you have only one electron, value will be 1. So all you have to do is to plug in all of the numbers and then calculate the energy.
More questions, sir.
Okay.
Use N-type materials in the electronic components, sir. If at all, if we use P-type materials, what will happen, sir? Why don't we use mostly P-type materials?
So instead of N-type, if you use P-type, what will happen, right? Is that your question?
Sir, yes, sir. If at all, if we use P-type material, what will happen?
So it obviously is going to depend upon what particular application you have in mind. So let me just give you some examples from the work we do. So we do some work where we are looking at some anti-reflective coatings on semiconductors. So there we are growing an oxide layer. So we have a thick oxide layer on top of the semiconductor, whether it is P-type or N-type. So in that particular case, nothing will happen, right? Instead of N-type, I have P-type. There may be some difference in oxide thickness, but the optical properties will not change much. But let's say I'm trying to build a device. So let us say I'm trying to form something like a Schottky junction between silver and my semiconductor. With N-type, I might have an ohmic contact, but with P-type, I might have a Schottky contact. So there, what I use matters, whether I use N-type or P-type matters. So eventually, it depends upon what application you are trying to tailor your semiconductor to. Okay.
Yeah, anyone else, please? Ma'am said. Ma'am said, please go ahead. Ma'am said. Ma'am said, please go ahead with your question.
I think it's
But I'm not hearing your audio, no. Vagdevi, please speak.
Yeah, please go ahead.
Can you explain how the PN junction acts as a rectifier?
Okay, so why is a PN junction rectifier? If you go back to your IV curve as far as the PN junction goes, you have current when forward bias and you don't have any current in reverse bias, right? So it conducts here and it does not conduct, which means if I connect it to a circuit, I'll only have conduction in one particular bias. So that is essentially the definition of a rectifier, which is why a PN junction is a rectifier. If you want a more physical explanation, you can say that in the case of forward bias, the barrier is lowered so that electrons and holes can essentially cross the junction. In the case of reverse bias, the barrier increases so that electrons and holes cannot cross, and that makes it a rectifier. If you look at the notes, we talk into much more in detail about how the band structure changes if you have forward bias and reverse bias.
How it occurs?
I'm sorry, what's the question?
How the energy band there is vacuum level? How it occurs?
Energy band diagram, how does the barrier occur?
Vacuum level.
It's not very clear. What about the vacuum level?
How it occurs in a
The question, so is the question, how does the vacuum level occur in an energy band diagram, or
how it occurs in a solid? How in vacuum level, how it occurs in solid?
okay, so how does vacuum level occur in solid, right?
Yes, sir.
Okay, so vacuum level doesn't essentially mean that it's a gas. Vacuum level is just an energy level which we define and say that electrons, when they have this much energy, they are essentially outside the solid. So vacuum doesn't necessarily mean that you have a gas or a vapor and you have an energy level. It is just an energy reference level beyond which electrons are no longer part of the solid. So it's not a question of how it occurs, it is an energy reference that we use when we describe these solids.
Ma'am said, please go ahead. Ma'am said.
Hello, sir.
Okay, please go ahead.
How can we say carrier lifetime is depending upon the dopant concentration?
So the carrier lifetime can also be related to the mobility. So mobility mu is nothing but E tau over m. So tau is nothing but m mu over E. So we have increased dopant concentration. So with dopant, mu will decrease, which means tau will also decrease. So you can use that equation and relate carrier dopant concentration to the carrier lifetime.
Thank you, sir.
Devi, please go ahead.
Hello, sir.
Yeah, please go ahead.
My name is Avna, sir.
Okay.
What is difference between platinum and gold, sir?
In terms of what?
Difference between platinum and gold, sir.
Platinum and gold, right?
Yes, sir. Difference, sir.
Okay. In terms of what property are you looking at?
What is difference between platinum and gold, sir?
Yeah, difference between.
Devi, professor has understood your question. Now, please listen to him. Please tell the class to be quiet. I find it very noisy.
Platinum is a semiconductor, sir.
Platinum is a metal, right? So platinum is a metal, gold is also a metal. So is your question the difference between those two?
What is difference between platinum and gold, sir? Platinum is a semiconductor or not, sir?
So platinum, if you're talking about the metal PT or platinum is essentially a metal. It's not a semiconductor.
Okay, sir.
Ma'am said, please go ahead.
Hello, good evening, sir.
Okay, good evening.
Tell me a few examples of semiconductor other than silicon, germanium, gallium oxide.
Okay, so you want something else that is not silicon or germanium or gallium arsenide, right? So let's look at a periodic table. So I have a portion of a periodic table here, so let me just write that. So now if you see, your carbon, silicon, germanium are all group 4. The ones to the left are group 3. You have group 5, group 2 and group 6. So if you don't like silicon or germanium or gallium arsenide, you can have gallium phosphide, which is a semiconductor, gallium nitride, indium phosphide, indium arsenide, indium stibide, and you can also form semiconductors between 2 and 6. So you can have zinc oxide, zinc sulfide, zinc selenide, cadmium, same way, cadmium sulfide, selenide or telluride. Mercury will also form a semiconductor with telluride, HgTe. So just by looking at the periodic table, you can sort of use it to construct or basically look at different semiconductor materials.
Okay, thank you, sir.
Thank you.
Good evening, sir. I am Kapoor Sundari from AMSET. I have a question: how we can calculate the conductivity where NC and NV are different?
So is it an intrinsic semiconductor or an extrinsic semiconductor?
Intrinsic semiconductor.
So intrinsic semiconductor. So once you know NC and NV, you can basically get Ni, right?
Yes.
And once you know Ni and you know mu E and mu H, then conductivity is nothing but Ni times mu E plus mu H times E.
Okay, sir. And if in case of extrinsic semiconductor, how we can calculate, sir?
So for extrinsic semiconductor, it's either N type or P type, right? So
Yes,
if it is N type, most of the cases, the electron concentration is much higher than the hole concentration. So you can ignore the holes. So conductivity is just Ne mu E. Same way for it will be Pe mu H. So that's how you calculate.
Yes. Thank you.
Thank you.
So one more from AMSET, please.
Okay, please go ahead.
Good evening,
Yeah.
sir.
Yeah, go ahead.
Rare materials other from germanium, silicon, but what is the reason they are less used?
So I will ask you another question. Why is silicon the most used? Why is silicon or germanium the most used? So you asked me why it is less used, right? So I'm asking you, why are they most used? So I'll give you a simple answer. If you look at the Earth's crust, the most abundant element is oxygen. The next most abundant element is silicon. Okay? So silicon is widely available as SiO2. If you want to call it sand, you can call it sand. So it's much more easier to extract silicon and use it as a semiconductor. So the main reason is the availability of silicon that makes it a widely used semiconductor. There are other electronic properties that are favorable, in that you can dope it and get improved properties. But from a simple economic point of view, the cost of the raw material is very cheap because it is readily available.
Okay, sir. Thank you, sir.
Sure, thank you.
Sir, what is the main difference of going for NPN rather for PNPN in a transistor, other than the mobility? So we prefer NPN mostly depending upon the mobility when compared to PNP.
Okay.
So other than that, any other?
That is what the reason I would think as I don't know if there's any other advantage in terms of fabrication. I would again answer based on the mobility. I don't know if there's any other advantage in terms of fabricating NPN over PNP.
Okay, sir. Thank you.
Thank you.
Good evening, sir.
Yeah, please go ahead.
Can heterojunctions can be used practically?
Yeah, so this was one of the questions you had answered, you had asked. So I've already answered it. The short answer is yes. If you look at the lectures from week 7 or week 8, where we talk about LEDs or lasers, they are essentially made of heterojunctions. So there are a lot of practical applications for these structures.
Good evening, sir.
Yeah, please go ahead.
Sir, you said electron travels faster than force, but when we connect P and N to forward and reverse bias, how the mobility is?
So again, it goes back to the question of the mobility, right? So usually electron mobility is higher. So mobility is nothing but it relates to how far the electron can travel before scattering. So if you use that as a measure, then electrons will travel faster than holes. So just another way of saying that electrons have a higher mobility than holes. Does that answer your question?
Yes, sir.
So how to calculate the absorption? Is that your question? Okay, so let me draw a direct band gap semiconductor. So we will pick gallium arsenide because gallium arsenide is essentially a well-known direct band gap. So this is my band structure. This is my valence band. And this is my conduction band. So because this is a direct band gap, my top of the valence band, EV, is right where the bottom of the valence band, conduction band, EC, and the difference is EG. So if I have light of some wavelength lambda, its energy is Hc over lambda. So if Hc over lambda is greater than Eg, then you're going to have absorption. And if Hc over lambda is less than Eg, you're not going to have any absorption. So that in a simple way is how you calculate. There's also things that go along with it. One of the assumptions here is that there is 100% absorption. So there is no scattering in the material. So whatever light that falls in gets absorbed. That is again an ideal assumption. In most materials it may not be a case. Some of the light might get scattered. But simply relating Eg to the wavelength, you can use it to quantify absorption. And this is true as far as direct band gap semiconductors go. Thank you.
From Placer City.
Okay.
Sir, I need to know why we are choosing only Boltzmann constant in solving problems related to intrinsic carrier concentration. Why Boltzmann constant?
So, okay, so your question is, when we talk about intrinsic carrier concentration, why NC/NV exponential minus Eg over 2kT, right? So Kb is the Boltzmann constant. So your question is, why is the Boltzmann constant come here? So there is a derivation for Ni. I'm not going to go through the derivation, but the derivation is nothing but the number of electrons is the occupation probability, which is f of E, times g of E, which is the density of states. So the Boltzmann constant comes because f of E depends upon the energy, and that dependence essentially has the Boltzmann's term. So we approximate this as exponential minus E minus EF by kBT. So this will finally feed back into Ni. If you look at the notes, there is a derivation where I at least show partially how this happens. We will not do the derivation here, but that is where the Boltzmann's constant comes from.
Good evening, sir.
Okay, go ahead.
Myself, Vignesh. I'm from KSRCT.
Okay.
My question is about diodes, sir. What's the major difference between homogeneous and heterogeneous diodes, sir?
So, the main difference, of course, is in the materials. So, if you have a homojunction, both my P and N are the same material. A heterojunction, it is not. So, this again leads to some difference in the band alignments. So, if I have a heterojunction, I should not only worry about the difference in the Fermi levels, but I should also worry about the difference between the conduction bands and the valence bands. So, you can have different types of alignment as far as heterojunction goes. So, if I were to draw this, so let me draw a homojunction. So, in this case, this is P, this is N. Both my conduction band and my valence band are aligned, right? So, this is your homojunction. Heterojunction, I can have different scenarios. I can have one scenario like this. So, I have the band gap of one material much higher than the band gap of other. This is called a type 1 heterojunction. I can have another situation where the band gaps are slightly staggered. This is called type 2 staggered. Or I can have a situation where the band gaps are completely misaligned. So this is called type 2 misaligned. So all of these different band structures are possible for heterojunctions, but not in the case of homojunctions. Okay? Sure.
Good evening, sir. I'm Archana from KSRCT.
Okay.
My question is, what is the significance of hopping conduction?
Significance of hopping conduction. So if you look at amorphous semiconductors, you not only have energy, you not only have electrons and holes that are possible in the conduction and valence band, but you also have these localized defect states where you can have carriers. So these are local states. So when they conduct, your electrons or holes will move from one localized state to another. So that is the process I call hopping. So that is called hopping conduction. So this means that these electrons and holes will also have a mobility. This mobility is much smaller than when you compare to crystalline semiconductors, but that is a way of conduction happening in these amorphous materials. So that is called hopping conduction.
Yes, sir.
Sure.
Sorry, MAM.
Yeah, please go ahead. MAM.
Sir, I am Bhuvaneshwari. What is meant by lattice match?
Lattice mismatch, right?
Yes, sir.
Okay. So let us look at growing a heterostructure. So if I think about it, let us say I have gallium arsenide lattice. So these dots essentially represent the atoms, and the lines are my atomic planes. So if I were to deposit more gallium arsenide on top, they will have the same lattice spacing. So let me call this lattice spacing as A0. So they will have the same lattice spacing, and that is how you form a homojunction. But instead of gallium arsenide, let us say I am depositing another material, aluminum arsenide. So aluminum arsenide has a different lattice spacing. Let me call it AS. But when I start to grow, aluminum arsenide will also try to grow following the same lattice constant as that of the substrate. So all of these are aluminum arsenide layers. So I have a material with some lattice, but it is being forced to grow with the same lattice constant as that of the substrate. So this is called epitaxial growth. But because I am forcing a material to either shrink or expand based on the substrate, I am going to have some strain that is built in. So this strain is defined by the lattice mismatch. So delta is your strain, which is nothing but the difference between the lattice constants of the two material divided by the lattice constant of the material that is being grown. So more this difference, more this strain, which means thinner is your epitaxial layer.
The Product has a question.
Yeah, please go ahead.
Hello.
Yeah, go ahead.
When two hydrogen atoms come together to form a H2 molecule, sir.
Okay.
Both electrons occupy orbitals, bonding orbitals.
Yes.
Can you please give the explanation about the bonding orbitals, sir?
So bonding orbital is nothing but where your electron has a lower energy in your hydrogen atom. So if I have two hydrogen atoms, each atom has one electron in the one-end shell. So when it forms a molecule, it forms a bonding orbital we call sigma and sigma star. And sigma has a lower energy, so both electrons go through. You can also show it in energy versus pH plot. So this is my 1s level, and when the electrons come together, this is my sigma, that's my sigma star, that's an equilibrium distance. Again, because energy is lower, both electrons go to the bonding orbital. I cannot have more than 2 electrons here because that will violate my exclusion principle.
Sir, in the lower section we have studied that the steel is elastic than rubber, sir.
You have studied what?
In our lower section we have studied that steel is expandable than rubber, sir.
Okay.
What is the explanation of it, sir?
So steel is expandable than rubber. Is that your question? Steel versus rubber? What your question is the elasticity of steel and rubber?
Yes, sir. Yes, sir. About elasticity.
Yeah, but we really don't cover elasticity as part of this course. I mean, you're asking this question in a wrong forum. I think you're more suited to a basic materials science class rather than a course on electronic materials. Okay? Because we never talk about elasticity as far as this course goes.
Thank you, sir.
Thank you.
Okay, sir.
Good evening, sir. I have doubt that is the doping concentration for doping all the elements are same or different?
The doping concentration depends upon how much you wish to add. So you can have it different. Usually it changes from material to material. It is controlled by you. So whoever is doing the doping can control it.
Thank you, sir.
Sir, as ma'am said already raised a question. Can you hear me, sir?
Yeah, please go ahead.
Sir, as ma'am said already raised a question. That is, NPN is very high when compared to PNP in terms of mobility.
Okay.
Okay, so it's equal for all the circuits.
I don't know with respect to specific circuits because I'm not necessarily an electrical engineer. I would argue again based on mobility it's better, but if there are certain reasons specific to electrical engineering circuits, I wouldn't know that.
Okay, so only the mobility characteristics or any other characteristics regarding the NPN and PNP is there?
So there might be differences in terms of practical fabrication of the devices themselves, but that is something that I will have to check. That I do not know.
Thank you.
Thank you. So Anyone else has any questions?
Thank you very much, sir, for answering all our students' questions.
Okay.
Thank you, sir. Thank you very much.
Thank you.
Okay, sir, do you have any questions?
Can you able to hear it?
Yeah, please go ahead.
Yes, sir. Our doubts has been cleared, and thank you for the kind replies. Thank you so much.
Thank you.
So I think we will sign off today.
Thank you all for participating. Thank you.